welcome to the next session. So we're going to be talking about quantum computing and specifically quantum advantage within quantum computing. What does the timeline look like? What are the implications? And we've got half an hour, so we're going to cut to the chase. So firstly, I have the job of moderating this panel. So I'm going to first ask the three panelists to please introduce yourselves very briefly, just kind of who you are, what does your company do, and kind of what do you think about quantum advantage? Like, how do we define that? If you want to start.
Yeah, happy to start. Hi everybody, I'm Hrant Gharibyan. I'm a CEO and co-founder of BlueQubit. We are a quantum applications and quantum software company, so we're excited to investigate how quantum computers that we have built currently or planning to build within the next 10 years, what kind of applications we can run on them, from quantum chemistry, quantum optimization to simulation. We also have a software product that focuses on simulating quantum circuits, quantum algorithms on GPUs, and with sophisticated simulation techniques, kind of pushing the barriers of what can you do with a classical compute to match the performance of current quantum hardware. And I think that's the way we will get to quantum advantage eventually, by exploring and doing numerical experiments.
Great, thanks. Andrew.
Hi, my name is Andrew King. I'm a scientist at D-Wave. D-Wave is a Canadian company that makes quantum annealing processors, and these are a specific type of non-gate model quantum processor that's particularly good at optimization and simulation of magnetic spin systems. We define quantum advantage as when you can do something better with a quantum computer than you can with a classical computer, and we reserve quantum supremacy for being able to do something with a quantum computer that you cannot do with a classical computer. And I believe we've already done that in specific simulation applications, and I can talk a little bit more about that. But basically, we want to broaden the reach of this kind of experiment.
Great, thanks. Nicolas.
Yes, hi, my name is Nicolas Daval. I am with Quobly, heading the engineering department. And in Quobly, we will make a quantum computer based on spin qubits out of the FDSOI technology. So we are very committed to go all the way to the quantum advantage with roadmap to the number of qubits we will discuss certainly that are needed for this quantum advantage.
Great, thank you. So Andrew, you mentioned, so you've defined quantum advantage quite narrowly as being better than a classical computer, and that you've already done that. Mm-hmm. Could you give us some more detail? I think people would be interested.
Well, actually, I meant supremacy, but I can give more detail on that as well. Not everybody likes that term, but I think that it's a lot more understandable and universal than quantum advantage, for which many people have different definitions. So specifically, the application that we demonstrated computational supremacy in was the simulation of quantum critical dynamics related to quantum phase transitions in programmable spin glasses. And so this is, if you hang out with too many physicists, you will say that this is a real-world application that people really need to do because they spend all their time thinking about it. And if you don't, then that's okay as well.
And in what sense is it quantum advantage? Like, what's better about the?
Well, I mean, you can determine the statistics of a system following some evolution of dynamics, and it's basically. It's impossible to do with any of the methods that we tried. We evaluated multiple state-of-the-art methods based on tensor networks, based on Monte Carlo experiments, and so on and so forth. And all of these experiments, claims of computational supremacy, have kind of many of them have fallen to spoofing efforts. So I can't yet guarantee that that's not going to happen, but we had an international team of about 60 researchers working on state-of-the-art techniques. And I think that we did a good job of really, really trying to solve it with classical computers, and we couldn't do it.
Nice, thank you. Nicolas, I just wanted to come back to Quobly. So you're a silicon-based quantum computing company. Kind of what does the timeline look like in silicon quantum computing?
Yes, so in what we are doing, I think the difficult task is really to make a good qubit in the semiconductor that you can get from a foundry that will make your chip afterward. So once you've done that, then we rely on this industry that makes billions of transistors all the same in order to solve this scaling problem. So the timeline is very much for our company that we've spun out of RTO in France, CLAT, with all the information to go see a foundry to say how they should do in order to make a good qubit. So we are in this process right now to make sure we can have these good qubits. I'm very hopeful that soon we will be able to publish on that. And once we have that, we will scale. And then the really passion discussion we have at Quobly right now is how it will compare to Moore's law, and how fast you can grow your number of qubits. In order to succeed, we need to go a lot faster than Moore's law. And what we think is doable right now is to go to 1,000 qubits in 2028, and then continue to grow and go to logical qubits by working with them. And we believe it will be in the early of 2030 that we can have something meaningful in the order of 100 of logical qubits.
Thank you. I think the audience would be interested. What's hard about getting to that 1,000 physical qubits? I mean, could you expand a bit? Why does it take 5-6 years to do that? What's the
what's hard is question that we have no answer about right now. When we will be able to densely pack qubits together, how much the crosstalk, the interference, and all this will slow us down in trying to go very fast. So I don't think there is anything published right now that can help us to see the difficulty of this task. So that's one thing. And the other thing is we will work to have a very powerful cryogenic roadmap to deliver a lot of cryogenic power in order for us to have all the control of our qubits in the same chip with our qubits. And that, I think, is an engineering problem of how fast can you go to 1 watt at 1 Kelvin and maybe to 10 watts. But that will be also required alongside with what happens when you densely pack so many qubits in silicon.
Yeah. And maybe just to stick on hardware a bit. So Andrew, I mean, D-Wave has been around for, 20 years now?
25 years.
25. So what is the next?
It was a pencil and paper company for quite a long time, but they've been making processors for at least 20 years.
And what does the next 25 years look like?
That's a good question. I hope to retire at some point towards the end of that. But I think that, the Advantage system that we had, it went online a few years ago, and that's got somewhere around 5,400 qubits. And the latest and greatest toy that I'm playing with right now has only 1,200 qubits. So it's not only about the number of qubits that you have, but it's also about the quality of those qubits. And you see the same thing happening in the gate model community, where it's not just about the number of qubits. What are the error rates, and what do your logical qubits look like? So we do have a gate model development program, which is not commercialized at this point. So we hope to commercialize that certainly in the next less than 25 years. There's some quantum annealing and gate model quantum computing have somewhat separate strengths. So I actually believe, and I'm not sure that this is a widely held opinion, but I believe very strongly that quantum annealing will continue to be the dominant mode of quantum optimization for at least 25 years.
And kind of over the past 25 years, kind of what have you learned in building systems that we can take forward? Like what's...
Yeah, that's a really interesting question, and I'm not on the hardware side, so I only can give a superficial answer to that, which is probably the best thing. Like the reliability of these cryostats, which we make superconducting processors, so everything has to be very cold. Reliability of these cryostats is really crucial for us because you don't want to be tinkering and recalibrating every time your fridge warms up. So it's become routine for us to be able to keep cryostats cold for multiple years on end without interruption. So also the I/O systems, you don't want to dump too much heat into the system, and like Nicolas said, you just have to pack as many qubits onto as a very small area as you can, and you're using fabrication methods that maybe have been used for other things, but not for superconducting qubits, for example. So you really need to refine your methods, your materials, and your fabrication processes.
Great. Maybe shifting gears a little. So, Hrant, you mentioned bringing together different types of computes within the solution. Is that kind of how you see the field getting to quantum advantage?
Yeah, that's a great point. I think the first algorithms I would guess, I would make a bet, that would be hybrid algorithms that will have quantum device programmed and kind of optimized with the classical feedback from amazing GPU and CPU systems that we have available. And kind of what gives me hope that we might see this in the coming years is how hard it's becoming to mimic like really coherent quantum systems that several companies like Quantinuum, IBM, Google, and others have built in a classical GPU simulator. Even with a lot of GPUs, the most sophisticated simulation techniques, it requires a lot of classical effort to try to mimic what quantum device is doing. And then it looks like we're entering a regime where we're gonna need to be clever to take advantage of this like Hilbert space that can be coherent and be manipulated, but the algorithms need to be adjusted to the right problem needs to be fit into it. So indeed, I think my perspective is that it will be some hybrid algorithm, perhaps variational, perhaps some quantum algorithms that will optimize quantum parameters from classical feedback.
Could you explain a bit more, why do you want to simulate a quantum computer? With a classical computer, I mean.
That's great. So you want to benchmark. There's a lot of algorithms and a lot of it in machine learning, a lot of heuristic methods for chemistry simulations that you cannot really prove whether the algorithm will work or not analytically. So the only way to actually know it will work if you want to run an experiment. And the ideal experiment is to run on a quantum simulator where it tries to mimic ideal noiseless quantum computer and maybe add some model of noise to really have controlled environment to see the behavior of the algorithm. And yeah, I think that's one of the primary reasons you want to do quantum simulation. Also, you want to do it to argue that whatever the quantum hardware can do now, you can actually get to that with the clever classical methods. That really drives the novel approaches to simulating quantum algorithms on quantum classical devices. That helps to really make sure we are in the frontier on both classical and quantum. That's the only way to really find the problems we can't do classically.
It's about trying to understand what quantum computers could do even before we have them.
That's right, exactly.
And so, I mean,
and project, how many qubits you will need to really see this exponential split between the compute.
So maybe next question for the whole panel. What are you most excited about in terms of applications of quantum computers? What are we going to use these first quantum computers for?
Good. Should I? Yeah, happy to continue. I think actually there's numerous applications from optimization to simulation to AI, machine learning, but I think the first problems quantum will solve will actually be fundamentally quantum problems in nature. I think I like Andrew's point that there might be very physicist-friendly problems, like condensed matter problems that are fundamentally quantum, that have a lot of entanglement, but have a lot of applications to building novel materials or understanding fundamental phases of matter that could lead eventually to designing molecules and in commercial use cases. But I think the first use cases will be quantum problems that will need quantum computers to solve.
And you, Andrew?
Yeah, I think there's a continuum between a quantum computer just being itself and doing some programmable simulation that is of independent interest, where you have arbitrary control over an arbitrary quantum system. And obviously we're very far from that, and I think it's very safe to say that in many modalities we've already achieved this. So the question is, how can you push along this continuum away from what you are just able to do because it's the easy thing to do, and towards things that are possible, but people are actually interested in it independently. And for me, these magnetic systems are a natural fit. So what are our main restrictions when we do these simulations? For us, we don't have a lot of control over the annealing protocol. So this is basically the schedule of how you tune the Hamiltonian. And the reason for that is our control versus our coherence is kind of marginal in terms of what we can do getting in and getting out without losing control of the quantum system. So if we improve the coherence by an order of magnitude, that vastly improves the set of things that we can actually do to manipulate this quantum system while keeping coherent control over it. So I'm excited to basically dumping a lot of energy, not physically into the system, but sweat equity, into meta-heuristics. So quantum optimization meta-heuristics that can be enabled by what we would call exotic annealing protocols. Now that might be a little bit in the weeds, but what I really mean by that is we have this quantum processor that is a unit, and it's going to be used as the inner loop of some computation. So we want to be able to use this as a really robust and flexible tool. And right now we're just very limited in what we can do with it. So I want to remove those shackles and just play with it.
And Nicolas, what are you excited about?
Yeah. Being in the hardware, I'm a little bit far from exact description of the application, but being excited on this would be certainly to see that with these new tools, people would use it in a way that we do not imagine right now. That would be very interesting to see, and then more on what Quobly's strength is. If we do what we intend to do, that having many qubits, then it's probably easy to make some great parallelism into our chip. So application where you need to have statistical data and a lot of reproducibility in what you're doing probably should run very well on Quobly's hardware in a few years.
So we're in the government track. What do you think government can do to help accelerate the timelines, or to how do people get involved in quantum?
Yeah, so first, my feeling is government are today doing really good at supporting and funding what we are doing. I'm coming from a different world in the semiconductor to this quantum. I see that we have a lot of national support and international support. What can they do better is it's a difficult question, but. I would say, I think it's already quite good. But
keep going is good. Right?
Yeah, I don't know. I'm interested to see what you can suggest.
Nicolas, go
ahead. Andrew, I think we're at an interesting point where there's clearly a lot of interest in funding quantum computing, and so there's a lot of money being put into it, and it's not always. Like the snapping your fingers to get the money from the government into the hands of, HR, who pays the researchers. So basically, I think that funding projects where national labs can work alongside commercial quantum computing companies, this is something that's really important. And it certainly happens, and sometimes it's a little bit slower than we'd like it to be. But national labs, they just have, it's an amazing program in the United States, and they have a lot of expertise that they can lend to work in concert with commercial companies.
Yeah, I will say things along the same lines. I think we see a lot of support from DARPA for instance, both on the hardware and like recently also in the algorithm side, as well as the DoD, NSF, a lot of like investments in quantum technologies. I think there was quite a bit of investment in the US in the past decade on the hardware side, and now I think there's several hardware platforms in national labs or on a private sector that you can actually test algorithms and do experimentations. And there's in a national lab level, there's also a push to get particle physicists to explore how quantum techniques, quantum computers can help their numerical methods, like traditionally particle physicists who did numerics. I think that's a great move. I think quantum computers are gonna be extremely useful in like driving fundamental physics, driving fundamental like chemistry, and yeah, I think it's great to see the investment, and I think the numbers are growing. Obviously, it needs to be strategic. I think there will be like bets, but certainly there's a growing interest in the past decade across different like countries. Yeah, in terms of like, one thing that, export controls come with those investments that could like restrict a bit collaborations among different countries. I think it's still, quantum is not there fully to be like much more restrictive. I think we're still in a like investigative and research phase that will take a bit longer to get to actually commercial applications.
So I often think kind of quantum's a space where people talk a lot about change, like change is really fast, things are happening really quickly, the industry's growing and so on. Like looking ahead in the next 5 years, are there things that you think just won't change, that are going to stay the same in this field? Maybe to any of you. Yeah, nothing. Is
I think 5 years from now, we're still going to be struggling with workforce issues, because I don't think there's any shortage of demand for quantum workforce, and everybody talks about at these conferences. Everybody talks about training up the quantum workforce and expanding the pipeline, and that takes time. And there's also kind of a greedy set of people on the other end of that pipeline who want to hire all these members of the new workforce. So I think it's still going to be a struggle to kind of expand as quantum companies, and this is one thing that I think we're going to be dealing with for quite a while.
Yeah, and maybe something that will not change also is our view of rapidly accessing our goals. So having this roadmap that says that everything is going fast, and quite probably we will see in 5 years that we have not progressed as fast as we wanted, but probably some good progress in 5 years still.
I was actually gonna say the opposite. I think to me, like, things are happening faster than I anticipated. I see a lot of platforms, like on a hardware side, being available and much better quality than what I would predicted a year ago. And I think that trend's like gonna continue. I think we're gonna see things happen faster than we expect. Like, for example, in error correction, I wouldn't expect several players actually passing the threshold with the speed they did, which is like a pretty impressive, and it's very promising that we are like moving to the next stage to actually make that error correction in much larger scale in a more useful algorithms. Yeah, I think in 5 years we're gonna still want more qubits and better like gate qualities. I think that's gonna take a while to get to really fault-tolerant quantum computers, but I think we'll see the first use cases. Like, we'll be much more confident that those devices can solve problems that are classically unsolvable.
I often feel like the thing that Moore's law really teaches us is that compounding improvements year on year make what 5 years ago looked impossible. They make things look magic, right? And I think that's the trend that we're seeing over the past now 2 decades in quantum computing. So maybe just last question to wrap up. If you had one wish, what would it be? How do we accelerate these timeframes?
Well, that would just go back to workforce, I think. A magical hiring pipeline where we get everything that we want immediately, and we don't have to compete with any other companies to get these people. This is what I would like, and just more hands on the keyboards and more hands in the lab.
Yeah, great.
Yeah, the team is everything. I fully agree with that, but I will add another choice that we'll have certainly a lot of technical barriers to break in order to succeed, and I wish that we do that.
Yeah, I'm gonna double down on education. I think I would love to see more quantum algorithms education in universities on an undergrad level, like people learning to program quantum. I think we are already like short on people. I think that you can do so many things with quantum languages and programming and the devices that is not many people know, and I think universities are fairly like slow. I think more pushing that to kind of support quantum expert quantum algorithm faculty who will build up the effort to start exploring what are you going to do with these computers once we've built them.
Great. So, I mean, we've heard about aggressive timelines in quantum computing to get to advantage. I think the demand for workforce is probably the biggest signal that this is really happening. It's an exciting time to be doing quantum computing. So please just thank me, or join me in thanking, you can thank me as well, but join me in thanking the whole panel.